All right. Good morning, everyone. So there were a great set of questions at the end of Wim's talk, which seg very nicely into what I'm going to talk about. So this is moving along very nicely. So what I'm going to cover is to try just give you a flavor or a feel for what it means to build quantum hardware. Where do quantum computers come from in a physical sense, and what the various aspects there are when considering different quantum computing hardware technologies. Because when you at least first enter the field, it can be quite confusing to see all the various different ways that people are trying to build quantum computers and understanding how they all relate to each other or fit together. So that's at least our goal for the next half an hour. It's obviously we can only really give a flavor or a touch of it, but that's the main purpose. And the first thing we're going to look at are something called the DiVincenzo criteria, which were a set of criteria laid out in the mid-1990s for what the criteria were that a particular candidate technology to build a quantum computer should meet. We'll then go through several of the most prominent quantum computing technologies, especially ones that have some commercial player behind them. So ones that you may see in the news often, that you may even have played with already, to try and understand the differences between each of them and what their strengths and weaknesses are. We'll then talk very briefly about something called quantum volume, which is an interesting proposal for a single number metric by which you can try and evaluate a quantum computing hardware technology. This is a very difficult thing to do, to have just one number to say, okay, this quantum computing hardware is good and this one is less good, or this one is really excellent. But this is the quantum volume proposal is one that attempts to do this, and is something that comes up repeatedly in the community now. So it's something that I definitely wanted to touch on at least. And then finally, we'll get to a little section where I try to expand on from a hardware perspective on some of the questions from the end of the last session of trying to predict the future, which is always pretty dangerous. But people always want to know, when will these machines and prototypes end up being useful? And to try and put some guesses at numbers out there. So before we get there, though, let's try and think a little bit about what makes a good quantum computer. So there are 5 criteria that were laid out by DiVincenzo, and in some sense, all of them are very intuitive and reasonable suggestions for what you should need. So let's go through them one by one. So the first one, a scalable system of well-characterized qubits, just means that you have a physical system where you can make not just one qubit, but you can make many of these qubits. If we're going to make useful computers, we need to have at least many of qubits for some definition of many. And as I said, we'll talk at the end about how many is. And the answer depends on what exactly you're trying to do with the machine. Number 2 is the ability to initialize. That also, again, seems kind of obvious. If you can't start your computer in a state with, for example, all the qubits in state 0, it's kind of difficult to predict what it's going to do. So you want to be able to initialize the qubits, typically all to the 0 state, but to some other state is fine too, just as long as you know what it is. The third is long coherence time. This is something that's maybe slightly unfamiliar in the classical world, but the analogy, if you haven't seen the word coherence before, or you don't know how to think about it in the context of computing, is think about this as like the memory time of each of the quantum bits. So in a classical computer, your memory, the classical computers really do actually have a memory time for bits. Just it typically tends to be so long that we treat it like it's infinite. In a quantum computer, this is, at least with present technology, not the case. Each quantum bit has a coherence time associated with it that tells you how long that state can store the value, in some sense, that it has. So Wim described a qubit as this vector living on a sphere, and if you imagine kind of it pointing in some direction on the sphere, the coherence time tells you something about how long you can wait before the position that it's pointing at is not really where it is anymore and it's become scrambled. And in order to exploit the power of quantum computers and quantum algorithms, you generally have to have the qubits stay coherent for a time longer than the time that your total computation is going to run. Another way you can think about coherence time, which is true at least in some of the qubit technologies, is that if you have a long coherence time, this generally relates to lower error rates for each operation you apply. It's not always true, but in many of the technologies this is true. So if you don't like thinking about the explanation I just gave of coherence time, you can, in many cases, just think of it just that's the error rate of each of your quantum operations or quantum gates. Which brings us to number 4, is you need a universal set of quantum gates. It turns out that in classical computing, the NAND gate is universal. So if you make a computer that only has the NAND or not AND operation, you can do any classical computation. This is something that generally comes up in first or second year CS or electrical engineering curricula. And in quantum computing, there's an analogous statement or theorem about a so-called universal set of gates, meaning any quantum computation that one can do can be done with a particular set of gates that are said to be universal. And if you want to have a good quantum computing hardware technology, your technology should be able to implement a universal set of gates. There are many different possible combinations of gates that are universal, but you need to pick at least some subset and be able to implement those. This involves both 1 and 2 qubit gates, at least. You can do it with more, but this is at least necessary. And we didn't talk at all yet, and indeed in the rest of this talk we won't make any great technical mention of what these gates exactly do, besides to say that you can typically think about at least the 1 qubit gates as rotations, and then the 2 qubit gates cause entanglement, which is something that will be touched on a little bit in some of the later talks. Then finally, the 5th one is easy again. You should be able to measure your qubits. If you do a bunch of operations on your qubits that carry out your computation and then you can't measure them, and measure the result of what happened, that's not very useful. So measurement is important too. So what we have on this slide is kind of busy, but what happened is we've listed a set of different quantum computing approaches, and it's certainly by no means all of the possible quantum computing approaches, because physicists have been busy over the last 30 years figuring out all the different ways that different physical systems could potentially realize a quantum computing hardware platform. And each of them is listed in each of these rows alongside the columns, which are the 5 different DiVincenzo criteria. And this table is actually something that came out from a roadmap from 2004 that we've just updated to reflect the current status. So if you download the report that's linked at the bottom there, you'll see the same table, except there'll be a whole bunch more red. Where red means no viable approach is known, yellow means we know of an approach, but it hasn't been fully experimentally validated yet, and green means there's an approach that is known and it's been experimentally validated. So thankfully, there's been a lot of progress in the last 14 years in improving the state of basically all the technologies shown here. So I won't try and go through each of these one by one. We don't have time for that to explain exactly why each of these little sort of color designations is what we've given it. And also I should mention that these are somewhat open to interpretation. We're trying to take a kind of complicated thing and lump it into 3 different colors, which is definitely, at least in some cases, one could argue for why is one this color or the other, but this is kind of a best guess at our interpretation of the landscape. And it's not a global truth by any means. So this is kind of a bit busy, so we can maybe simplify a little bit, and instead of trying to do it by all 5 DiVincenzo criteria, let's maybe just look at it in terms of three sort of simpler categories. The first is coherence, the second is scalability, and the third is control. And one of the things you can see here is that the superconducting circuits technology is one where we have green for all three. And this is one of the reasons why there are so many superconducting circuits commercial efforts. That technology has reached a level of maturity where, at least for building small and maybe medium scale machines, all three of the major things that your technology has to satisfy are satisfied, and it's become a question of putting in a lot of engineering effort to build machines of larger scale. And then there are a number of other technology approaches that you see in this list, and you can see they range from red, where we have no idea how we're going to scale this, or at least it seems hard to, through to ones where there's a gradient of color, where that means it's kind of a gray area. Maybe it's been close to demonstrated, maybe it's more just proposed, it's sort of more open to interpretation. One I'll especially point out that's like that is oh, these ones are actually flipped, is the Majorana fermions. Those ones should be red through green, and the reason for this is that there's a lot of press about Microsoft's efforts to build Majorana fermion qubits, and these seem like a great technology that's going to be, or at least has the potential to have a big impact on the error correction overhead that one has, but they haven't demonstrated a single qubit yet, so it's difficult to evaluate kind of, is this no approach is known, or how do the experimental demonstrations that have been done so far connect with it? So this is one where there's really a lot of kind of unknowns, whereas something like superconducting circuits, it's much more known. People are building commercial hardware with it right now that you can actually use. So let's try go through in a little bit more detail what at least some of these technologies actually are. So like I said, one of the most prominent technology approaches is superconducting circuits, and this is an approach that is being pursued by, amongst others, Google, IBM, Rigetti, Quantum Circuits Incorporated, D-Wave, Intel, and others. Those are just some of the commercial entities engaging in this, and there are more, as well as many different academic efforts. So this is a very popular approach, and for good reason. And mainly what I'd like to get across on this slide is a flavor for kind of what these devices even are. So this picture here is from Google, but many of the other devices from the other vendors look relatively similar. And the basic idea is that you have an electronic microwave circuit, which would not look too unfamiliar to a classical microwave analog engineer, that has a series of, or set of essentially nonlinear LC oscillators, where each one of those nonlinear oscillators forms a qubit, at least in many of these implementations. It turns out that there are different ways to build these qubits, and some of them are not exactly a nonlinear oscillator, but at least many of the vendors, what they're doing can be thought of in this way. And the key element between all of them, though, that is universally true is that they all involve a nonlinear element called the Josephson junction. And this is providing the core of how you get a qubit out of a device that is otherwise just a circuit. The other thing that's crucial about them, what you can see directly from the name, is that they're superconducting. If you took a regular classical microwave circuit at room temperature, it would not be superconducting. And this is important because the dissipationless transport of electrons allows the maintaining of a coherent state that, or maintains coherence in the system that allows you to have a good qubit. At least it helps to fulfill one of those DiVincenzo criteria. Another one of the reasons people really like these systems is that because it's, in some sense, looks just a circuit and is almost something that you can build with a standard CMOS process. It's not exactly at the level where a standard CMOS fab can build it, but it's close, is that a lot of the technology that's gone into making CMOS processes in the classical world scale enormously can be leveraged to help scale this technology. And so we've seen very rapid progress that we'll show a little bit later about how quickly these ones have grown. So another technology that's really interesting that is also semiconductor-based are electrically controlled quantum dots. And these ones are arguably even more similar than superconducting circuits to how current classical computers are built, because they look almost, if you squint, like how a classical transistor looks. Typically what you have is you have some semiconductor material, you make a heterostructure that has a kind of stack of two slightly different semiconductors where electrons will like to live in the top layer. It's a so-called 2D electron gas. And then you can pattern metal electrodes on top, which i.e. are just wires. And you can make electrostatic fields with those wires that allow you to trap single electrons. And then you can use the spin degree of freedom of the electrons as qubits. Or you can have multiple qubits together, and each of them has a spin, and then sort of collectively amongst the 2 or 3 or 4, their collective spin can be used as a qubit. It depends on the exact scheme people are doing. This is an approach that Intel is also investigating, along with several other companies, as well as many people in academia. And one of the most interesting aspects of it is that it's, again, very close to how a current CMOS classical processor is built, so it seems like one where the potential for scalability is there. Another technology that has a number of commercial entrants is trapped ions, and this is a very interesting technology that looks pretty different from the previous two. There's no longer a semiconductor chip that is somehow fundamental to forming the qubits in this one. The idea here is that you take ions, which are atoms where you've stripped off one electron so they're positively charged. You take ions and you can trap them with electromagnetic fields, and then you can manipulate them with either microfields or with lasers. And these qubits are, I think, especially interesting because of their coherence properties. Sometimes the ion trap people like to talk about how these are kind of God's qubit because it's an atom. It's almost the perfect thing you could get. Some people may quibble with this description because then you're doing something with it, so now a human is involved again. But nevertheless, they do have really great coherence properties, and they look like they're going to scale to sort of at least reasonable numbers of qubits in a single trap, maybe somewhere between 30 and 100. So these are going to be really interesting for the next few years. IonQ is one of the commercial entities exploring this, as well as Alpine Quantum Technologies. Another related technology is the use of also individual atoms, but instead of ions this time, they're just neutral atoms, i.e. atoms where you haven't stripped away an electron. And the idea here is you can trap these atoms in space, either using an optical lattice where you have interfering laser beams from multiple directions, making this egg carton-like potential that the atoms will live in, or you can do it with optical tweezer arrays, which have become very popular the last couple of years. And there's now at least one commercial entity I know of that's exploring this. I think there may be more coming up soon, and certainly there's a lot of academic groups out of which these entities can spin it. So this is, again, kind of interesting because it's natural atoms, so the coherence properties can in principle be really good, and people have made a lot of progress in the control engineering for this in the last, even I would say, year. Another approach that people often talk about, and it appears in the media fairly often, so we mentioned briefly, is defect centers in diamond. So if you have a crystal of diamond and you knock out one of the carbon atoms, and you replace it with a nitrogen, and then you knock out another neighboring carbon atom, so it's a vacancy. You get something called a nitrogen vacancy center. So it's basically a color center in diamond. It has an effective spin that you can use as your qubit. There's a lot of work in academia on this. I'd be happy to chat afterwards with anyone about if you're curious about kind of what the major challenges to scalability are with this. I think at the moment it's fair to say that it has pretty significant scalability challenges, but maybe not insurmountable. Nevertheless, at this point, I think less commercial interest than in the other technologies we've covered. We get now to Majorana fermions and fractional quantum Hall states. This is a technology that especially Microsoft is pushing, but Bell Labs also has a long history in this, and is a really interesting technology that is still rather unknown where exactly things are going to end up with this, but if it works, will be amazing. And the very rough intuition for what's special about this is that this approach takes advantage of topology. So this notion that objects don't just have a geometric shape, but they can be characterized in kind of layman's terms by how many holes you have in the object. So if you have a coffee mug, you can deform that into a donut, and it preserves its topological state because it still just has one hole in it. Whereas if you have a sphere, like a golf ball or something, if you wanted to turn that into a donut, you'd have to do something very aggressive to it to make a hole in it. And this is the intuition is that if you store your quantum states in objects where the state is represented by the topology of this object, it'll be more robust to fluctuations or noise, because a little bit of changing of the geometry doesn't matter. You have to do something really harsh to it to get to change its topology. And I'll defer more detailed questions about this technology to speakers from Microsoft, who I think are speaking today and maybe also tomorrow. So there's another then, now we've left the world of matter qubits. It also turns out you can make quantum computers from photons. And there are at least 2 commercial entities exploring this, Xanadu and PsiQuantum, where the idea is that you have some chip, or it could potentially be a free space setup, but typically people doing this on chip, where you send single photons or squeezed states of light through the chip, and then you measure with single photon detectors or number resolving detectors if you have them, and you can perform quantum computation based on so-called cluster states that get produced once you send photons through this network of beam splitters, which is depicted in the picture there. I think this is also a fascinating approach, and it will be very interesting to see how it plays out. For those who want to learn more, Terry Rudolph at PsiQuantum has a great review article with the title something like "Why I Believe in the Silicon Photonic Route to Building Quantum Computers," that I think really summarizes nicely the state of that field. NMR was one of the original approaches to building quantum computers. I think at this point it's more or less consensus that it's very difficult to scale, and that we won't likely see very large NMR quantum computers anytime soon. But I thought I'd bring it up just to mention it, because if you kind of Google for quantum computing and IBM, for example, you'll probably get a press release from 2001 saying, okay, demonstration of a quantum computer in an NMR setting. And so this was a thing, now it's less of a thing. So where do all of these platforms stand right now? Like I said right at the start, it's kind of hard to quantify systems that are so complicated, and there's so many different metrics for what it means to be good. So this slide is just one metric. It's just number of qubits, which I should emphasize is not the only important metric. There are other metrics that are crucial to how good a quantum computer will be for running your particular problem. But this is one number that everybody can understand and is also an important number. So we have number of qubits, and then basically by the organization making it where I think in this slide only commercial organizations are listed. So we've also broken it down by who's actually built a system and commercially released it, so people outside of that company can use it. You can see there's IBM, D-Wave, and Rigetti. And these are all superconducting circuit approaches that are being taken there. And then we also have categorization of built but not yet released, where built basically means there was a press release saying this has been constructed with no details yet of exactly what it does. But and in that category we have Google and Intel, and you can see all of these so far are superconducting circuit approaches, and then there are all the other approaches at this point are still, I would say, in a research phase or commercial research development phase. So one of the things that's really interesting to look at is how the progress in these fields has happened. And this slide shows just two technologies. It shows superconducting circuits and trapped ion qubits. And it's kind of remarkable to see the progress that's happened, and it somewhat explains why we see so many superconducting circuit efforts and why they are so advanced, as well as why we see trapped ion qubits being explored commercially. That the y-axis here you can think of as the error rate. It's also sometimes called the fidelity or the gate error, as a function of time for these different technologies, where each data point is some paper where people put out a result saying we did this differently and we achieved this new error rate. And you can see that all the error rates are decreasing exponentially as a function of time. So it's almost like a Moore's law for superconducting qubits and trapped ions, where critically some of the technologies have even gotten beyond the 99.9% fidelity point, which is really a fantastic achievement. So as I said, this notion of just one number to rule them all is a very difficult thing to do, but at least the proposal from IBM is something called the quantum volume, and it tries to take into account the two things we saw on the previous slide, both the number of qubits you have as well as the error rate you have, as well as considerations about the architecture, about how the different qubits are connected to each other, because that also affects the capability of the machine. And so this is, like I said, an attempt to have one number that is a metric that by which you can understand and compare different machines. So this is definitely something to watch out for. Then finally, we get to the dangerous part of trying to guess the future. And so if you want to know when will any of these hardware platforms be able to do X, Y, or Z, as Wim already explained, you have to think about both what the classical competition can do already, as well as how long your circuit is once you've done the mapping to a quantum algorithm, and what the number of physical qubits you need is to implement that algorithm, and the circuit that underlies it, and the circuit depth has an impact on the required fidelity of especially the 2-qubit gates. Those are typically harder than the 1-qubit gates. And so these numbers here all have a number of assumptions behind them. You can question the assumptions. Maybe the assumptions are even wrong. But they're our current best guess of where things are going to be. So the first line in this is quantum supremacy, which means is taken to mean a quantum algorithm that performs a somewhat contrived task that is designed to be easy to do on a quantum computer, but very hard to do on a classical computer, such that if you build a big enough machine, in this case, one of the estimates is 49 qubits, that you will be able to do on the quantum computer something vastly more fast than you can on a classical computer, such that there will be no debate that the quantum computer did actually massively outperform the classical competition. So this is something that especially Google has done a lot of work on, figuring out the theoretical bounds and what you need to have done there in order to achieve this, and many people are racing towards. The next one in this list is QAOA, which we'll have an entire talk on later today, but this one is really a guess. It's for doing quantum optimization. How many qubits do we need to imagine getting a performance advantage? It's not really known, but I think a reasonable guess is maybe around 100 qubits and a 99.9% fidelity. But it's a guess. Quantum chemistry, we've also talked very briefly about already. And this is, again, something where it's also unknown exactly how it's going to be, but people suspect that somewhere around 100 qubits, and maybe you need around 99.9% fidelity, but maybe more, you'll be able to, you can at least imagine a situation in which you get a quantum advantage from running this quantum chemistry problem on a quantum computer. Then the next category of applications requiring error correction, you see a massive jump. And this is the case of something like Shor's algorithm, which is famously an algorithm that really put a lot of energy into the quantum computing community because of its security implications. But this is something that is an algorithm that actually is a pretty long circuit, and you won't be able to get away with, in all likelihood, of running a machine without error correction that will be able to do this. You will need a machine that can correct errors, and you can't just assume you'll run it and no errors will happen during the computation. So this is there's a big overhead to error correction in almost all schemes. The one exception that we know of is in the case of Majorana fermions, the predicted error rates are sufficiently low that the error correction overhead will be lower. But for basically every other technology, the best guesses are that to run Shor's algorithm to crack a code that would be actually interested in cracking something like a 1024 or 2048-bit key, you're probably going to need somewhere north of 50 million physical qubits and a relatively high fidelity. So that one we would say is longer term rather than near term. So with that, thank you very much for your attention. I'll be happy to take 1 or 2 questions if we have the time. And there's the QR code while we're at it.
You mentioned Shor's algorithm, 1024 million qubits with 99.9% fidelity. Could you give some sense of the scalability, right? Because we're up to 4096 right now. How many qubits it might take?
Sorry, could you say the last part of the question?
As we scale up the number of bits in the key size, 2048 to 4096, could you give an indication or some feeling for the scalability and the qubit size?
I see. So from what I recall, it was, you basically needed enough qubits to be able to fit the number multiplied by 6, I think. So I think it's something like, I think it's growing linearly. The number of logical qubits you need, and then the number of physical qubits you need, then it gets a little tricky because it's not just necessarily linear there, because if you need to go to the next level of error correction and add a whole nother, there's some stepping points, so then you need to actually do the detailed architecture analysis. But kind of best case scenario is linear, maybe it's worse. And I think we're kind of short on time, so maybe one more question, then we'll move to the next speaker. The lights are blinding me here, so whoever has the microphone can, if they can.
Peter, I have it over here. On your last slide, with the exception of Shor's algorithm, are there algorithms for each of the rows you presented in the slide that would enable us to tell whether we've achieved quantum supremacy, et cetera?
So evaluating whether you've really thoroughly beaten the best known classical algorithm, I think, is going to be a challenge for the community for the next few years, because benchmarking is always tricky. And normally what happens is someone will run something, they'll do some calculation, and maybe they think they've managed to beat the best classical state of the art, but they didn't really know, or they didn't really know what it was. Somebody else somewhere in the world had another classical algorithm that was actually really good for that, or was a small tweak on another one, and so then it kind of leapfrogs back and forth. And I think in the case, especially something like optimization, where it's there's so many people working in classical optimization who have lots of clever tricks, that there can be a lot of back and forth of like, well, I found a problem where it seems like the quantum computer is doing really well compared to these solvers I tried, and then you release it, and then somebody else says, well, actually, I can make another solver that works a little differently that can beat it. And so I expect there'll be back and forth there. And I think a big part of kind of which, for each application, how that's going to go will depend on the maturity of the classical algorithm landscape. Like in the case of quantum chemistry, I think there's a big community that does things mostly in a standard way, from how I understand it. and that if you can do one of their benchmark tasks faster, there'll be a much more quickly accepted quantum supremacy result there than there would be in optimization, where there's so many different ways of doing things, it's kind of unclear whether you've really beaten the state of the art because you've only tested a few things. Cool. So with that, I think we need to move on.